Hello everybody, this is the second video for chapter 3 of the statistical learning course. We will pursue the discussion we had in the previous video about model selection. Okay, so in the first video, we discussed shortfalls of the k nearest neighbors method, and then we said that linear regression addressed some of these. So for example, k nearest neighbors provided prediction functions that were in smooth, whereas a linear regression provides smooth, well, in fact, linear prediction functions. But we also mentioned that linear functions sometimes are too inflexible if the relationship between predictors and the response variable are nonlinear. So then we discussed transformations that could be applied to original predictors so as to capture nonlinear linear transformations. So we proposed or we illustrated the case where we took polynomial transformations of a single predictor to be able to perform polynomial regression and capture uh, relationships between the response and the predictor, which are of the polynomial form. So then the final question we investigated is how do we select the order of the polynomial within the regression? Should we use 1, 2, 3, 4, 5, 7 terms? I don't know. So to do this, what we suggested is to use the same technique than what we introduced in chapter 2, which is to use either cross-validation or at least a validation set to perform out-of-sample performance assessment and select P, the number of predictors or the order of the polynomial, which minimizes the out-of-sample mean square error of prediction errors. So, as we mentioned right at the end of the video, often historically, performing cross-validation was very cumbersome. So other techniques were proposed instead to make the performance assessment convenient. So these other techniques that we will discuss, they require only one data set, which is the training set, and they attempted assessing the performance on that training set. Now, if we only consider if we have various models with various levels of flexibility, and if we pick the one which has the highest accuracy in our training set, of course that would always be the most flexible model. So for example, in KNN, this would always be k is equal to 1. If we have a linear or polynomial regression, we would simply choose always the largest possible p. So this approach is not satisfactory. Okay, we cannot only take the most accurate method in sample. We need to have some form of parsimony criterion incorporated within our optimization scheme to avoid overfitting. Okay, so models which have too many parameters should be penalized some way, otherwise they will systematically be selected and your prediction model will systematically overfit your data. So these methods that were developed historically based on a single training set, um, sometimes you might recognize their acronyms. So AIC stands for Akaike's criterion. AICC, it's a modified form of the Akaike's criterion. Here, BIC is the Bayesian information criterion. Both of these are metrics which represent a trade-off between accuracy and parsimony of a given model. So to select the suitable amount of flexibility for a model, this criterion suggests using the one that is not the most accurate in sample, but rather that offers the best accuracy parsimony trade-off. Okay, so we'll illustrate how they work. So let's start with Akaike's criterion, AIC. I'm sorry, I'm not sure how to pronounce this guy's name. It's I guess it's Akaike's, but I'm not sure. I apologize for that. But this Akaike's criterion is meant to reflect, as we said, a trade-off between parsimony and accuracy. So the Akaike criterion for a fitted model is defined as 2 times p, where p is the number of parameters in the model, minus 2 times log of L, where L is the likelihood of the trained model with optimum parameters, so the optimal likelihood that is provided by fitting the model and optimizing its parameters. And here we have minus 2 times the log of L, so log of L is just a log likelihood, and we have this criterion here is defined like that. So when we use the Akaike's criterion to optimize or to select a model, we want to find the model or the amount of flexibility which minimizes this quantity. Okay, so why do we want to minimize this? Well, ideally, this 2p, it represents the number of parameters. So if we want the model to be parsimonious, we'd like to have a number of parameters that is as small as possible. So ideally, we'd like this to be as small as possible. But if we want the model to be as accurate as possible, we want the likelihood, and thus the log likelihood, to be as large as possible. So because there's a minus sign, this whole minus 2 log L, we'd like it to be as small as possible. So here we want to select models which provide an AIC value that is as small as possible. Now what's going to happen if a model is very flexible, so it has many parameters, both terms should be large. Okay, so as well, 2p will be large because you have a lot of parameters, but this will also be large because you fit well. But hopefully, if the model is too flexible, this term should be much bigger than this one, so you'll be penalized by this term. Conversely, if you're not flexible enough, you won't be penalized much by this term because you have a low number of parameters, but this term will penalize you a lot because your likelihood will be very small, so minus the log likelihood would be very large. So for the suitable trade-off, we hope that both terms are kept reasonably small. Okay, so this is just repeating what I just said. So by minimizing the AIC criterion, finding the amount of flexibility, or for example, right value of P or right value of capital K for K and N, the retained model will be the one minimizing the AIC, so it should offer them the optimal, a good trade-off, strike a good trade-off between parsimony and accuracy. Okay, so now this was for the AIC criterion. There exists a plethora of other similar criteria that were developed in the literature, and these criteria, they mainly differ by assigning different values or different penalties for the parsimony. Okay, so here the corrected Akaike's criterion is defined as the original Akaike's criterion plus here 2p plus 1 divided by n minus p minus 1, where n is the total number of observations. So we see here in the AIC model, the penalty was not impacted by the number of observations directly. So of course, the number of observations would impact the likelihood, but there's no n appearing in the penalty, where here we see that adding this value here adjusts the penalty for the sample size. So we can see that a different penalty for the parsimony is assigned for AICC than for the regular AIC. And similarly here for BIC, the penalty also has a different form. So the penalty is log NP instead of being 2p as in the AIC criterion. Okay, so now which one to use in practice? Is it better to use the AIC, AICC, BIC? Well, personally, I find it's very subjective. So all these criteria, they have some theoretical underlying justification, which we won't review here, so this is out of scope. But nevertheless, we see that there are different penalties assigned to parsimony. So if you use different criterion, you might get a different retained model. So my personal opinion on this is it's somewhat subjective which one to use. It's good to try like one or maybe a few of them and see if you always get the same model. So if all criteria give you the same model and say this is the best one, well, then you have high confidence that you can proceed with this one. But if you try the various criteria and they all say different things about which model should be retained, then it's not as clear. But this, we see that this is an advantage of using cross-validation instead of these more traditional criteria, because cross-validation, you have only one value here that you obtain, which is different than here. If you use other criteria, you might get different optimal models, so it's more subjective in a sense. Plus, although these criteria have theoretical justifications for the penalties, these justifications are typically asymptotic in nature. So and we work in finite sample. So the cross-validation or out-of-sample performance assessment directly measures for finite sample your prediction performance. So not only it's less subjective, but it has a more direct relationship with what we're really trying to measure, unlike these criteria where the penalty assigned to parsimony does not have intuitive representation or depiction. Okay, so as we said, the AIC, AICC, and BIC, they assign a different amount of penalty for non-parsimony. So for example, AICC and BIC, they penalize much more heavily a lack of parsimony than AIC. So depending on which criterion you use, you might favor more conservative models, which tend to be more simple, or if you use the AIC, maybe you'd allow for a bit more complexity in your model than the other. Okay. So now this is we discussed the shortfall of these more traditional criteria, but the advantages is that it's much quicker to compute the AIC or BIC than the cross-validation MSE. Because for AIC, for example, or the other criteria, you only need to train the model once on your training set, and then this gives you the quantity for the AIC directly. Okay, so if you use tenfold cross-validation, for example, you need to train the model 10 times to get your MSE. Whereas for AIC, you need to train it once. Okay, so if you need to do a lot of computations pretty quickly, it might be a reason to favor these more traditional criteria for model selection. So nowadays, in like recent machine learning approaches, out of sample mean square error is often preferred to AIC, AICC, and BIC because computing time becomes less and less an issue, in the sense that like standalone computers are more powerful and there's more technology to aggregate the computing power of many machines at the same time. So as time goes by, out of sample mean square error becomes more and more accessible to assess the performance and to do some model selection. Okay, so it's more and more accessible, but still some people use these more traditional criteria in certain circumstances. So for example, we will see subsequently methods to select predictors within a model. So for example, if you have a linear regression, of course you can, and you have 30 predictors. Of course you could try to use them all, but this might often lead to overfitting. So you'll need methods that we'll discuss later on to select which one of the predictors should be retained. So to do that, an approach would be to consider various combinations of predictors and assess their fit. So if you do that, for example, if you assess the quality of the fit for various combinations of predictors, and if you use your performance evaluation method is out of sample MSE, so not only you need to train the model 10 times if you use 10 times cross validation, but you need to train it 10 times for each possible combinations of covariates. So this leads to a very extensive amount of training of models, which might be prohibitive. So for this reason, even in some circumstances, so for example, when you do feature selection, or you want to select which explanatory variables are included in some regression model, still there's room to use these more traditional criteria if you want to save computing time and get results more quickly. Okay, so these traditional criteria are quicker, but this one, the out of sample MSE, if you're able to use it, it might be better because it, as we discuss it more, it measures more directly what we're interested in, which is predictive ability for unseen observations. Okay, so if we go back to the previous polynomial regression example, then the various models which we could consider have a logical order. Okay, so the first model is only include x, linear regression. Second model include x and x squared, quadratic regression. Third model include x, x squared, x cubed, cubic regression, etc. until some maximum degree or order p. So then you would have exactly p models to train. Okay, so the first model would be this one, second model this one, until here the pth model, which is this one. Okay, so you have exactly p models to compare. Okay, to train. So for that reason, well, here we see that the number of models to train is linear with the order of the maximum order of the polynomial you would consider. Okay, but in many prediction problems, so let's say you have a linear regression, there's no natural order for predictions. Okay, so if, for example, you want to predict the height of somebody and you use as predictors his age, his gender, and I don't know, the length of his arm, let's say something like that. Well, there's no natural order for the predictors. Okay, so the first predictor to include, it might be only the age, it might be only the length of an arm, it might be only, what's the third one I said? It's the gender. So there's no order for inclusion of covariates or explanatory variables. So in this case, the total number of models that should be considered during the training is not p, it's 2 to the power p. So each explanatory variable could be either included or excluded. So you have two choices for each variables. And because you have p variables, you have in total 2 to the power p model when there's no order, logical order for predictors. This is different than for the polynomial regression, where you have p models to train instead of 2 to the power p. Okay, so let's say you have 100 predictors, a very high dimensional regression setting. How many models are there? Well, this gives 1.26 to the power 10 to the 30. Okay, so of course this is way too many models. You cannot train all of them because it would take too much time. It would take you like billions of years probably to compute the performance of all such models. Okay, so often when you have many predictors in a regression setting, you want to know what's the optimal degree of flexibility you should get. So select only determine how many predictors you should retain, and out of the predictors which one you should retain. Okay, so let's say you have 30 predictors. Maybe at the end you want 5 predictors, and you want predictor A, C, D, and Z, or whatever. Okay, so you don't want to retain all of them. So you need to find a suitable way to determine what are the predictors that should be retained in my model, and testing all possible combinations. If you have too many possible choices, so too many predictors, it's infeasible. So how to do that in a more reasonable time frame that is feasible in practice? So this is what we're gonna study next. But before, let's just repeat the rationale why we want to do that. So if some predictors are irrelevant in the regression, so let's say you regress your response y on predictors x1, x2, x3. Let's say x2 has no impact on y. Okay, so there the y is just independent from x2. Then, so one thing you could say, well, I'll still be regressing y on beta 1 on x1, x2, and x3, and hopefully the coefficient for beta 2 should be very close to 0 because it has no impact. Okay, but nevertheless, if you do that, the coefficient for beta 2, it might be small, but it's not going to be 0 exactly. Okay, so because of that, this will generate noise and generate variance in your prediction. And we saw that variance is one of the components of the mean square error of prediction for new observations. So the idea is you want to reduce the variance of your predictions as much as possible if they don't contribute to reducing the bias. Okay, so here, if x2 doesn't impact y, integrating x2 in your prediction model will only generate noise and variance, but it will not help reducing the bias because it has no impact on prediction. So you'd rather try to filter out this variable x2 from your analysis to get better predictions. Okay, so the purpose of removing irrelevant predictors from linear regression or other regression models is to try to reduce the variance of your predictions so as to reduce the expected square error of predictions for new observations, as we've seen in chapter 1. Okay, so we don't want the model to be too flexible and incorporate too many predictors if some of them are either irrelevant or have very low relevance and just contribute more to generating noise than capturing genuine prediction patterns. Okay, so let's say we have, again, a regression model with p predictors. We said that if we want to consider all possible combinations of predictors, we have a total of 2 to the power p models to consider. Okay, so this is too much. So the idea here is, instead of comparing all 2 to the power p combinations, we will have to select a subset of such combinations. Okay, so we cannot try them all, so we'll try a few of them to see how they perform. Okay, but now, how to determine which subset of combinations will we consider? The textbook, the textbook, but it's a very traditional statistics procedure, entails using a stepwise approach. Okay, so the textbook suggests to use that stepwise approach, which we will study subsequently. Okay, so there are three types of stepwise approaches: the forward approach, backward approach, and hybrid approach. So we will illustrate more thoroughly the forward approach, but the backward and hybrid, once you understand the forward approach, these two are somewhat have many similarities, so it's going to be straightforward to understand the last two. Okay, so let's illustrate the forward approach as a way to understand the stepwise methods for variable selection. Okay, so let's say we want to apply a stepwise approach to select the suitable predictors in the regression model. The first thing we should do in pursuing the stepwise approach is to determine a criterion to assess the performance of a model. Okay, so we have to say, okay, the performance of the various possible models. So when we say various possible models, it means various possible predictor combinations. We have to say, okay, what criterion will we use? We could use, for example, out of sample MSE or cross-validation MSE. So if you have a lot of computing power, or if you don't have too many predictors, then this is a very sensible approach, okay? Because we saw earlier that this can be a very good criterion. If you have less computing power, or you have many predictors, then maybe you could use AIC, AICC, or BIC as the criterion to assess the performance of the various models, etc. Okay, so these are examples of criteria. There might be others, but just for now, let's assume we take one criteria, fix it, and then this is what we're going to use. Okay, so what we assume here is the higher the performance in terms of these criteria, the best. Okay, so, and the keyword here is higher. So we want to maximize the performance. So the performance will not be the MSE, the performance will be minus the MSE, okay, or minus the AIC, okay? And we want to maximize the performance by minimizing the MSE or AIC. Okay. So just a bit of notation before formally describing the algorithm. Then for m equals 0, 1 until p, we will denote p I1 IM, the performance of the model including predictors I1 until IM. Okay, so p I1 IM is your criterion. So for example, let's say it's the AIC. Okay, so p I1 until IM, it's the AIC for the model, which includes a subset of predictors, which is where the first predictor is denoted I1, first predictor included is denoted I1, until the last predictor included being denoted IM in the model. Okay, so how does the forward approach works? So the forward approach, it's a bit like Occam's razor for those who know about this concept. So we want to have a model as simple as possible, but not more. Okay, so we start with no predictors included in the model. And what we're going to do, so we're going to add a predictor to the model if and only if the addition improves on the performance. And then as soon as the performance cannot be improved more than or further, we're going to stop adding predictors to the model. Okay, so in the first step for the forward approach, we start with 0 predictors included in the model and compute P. So this is the null set, which means that we incorporate no predictors. Then, once we calculate the performance with no predictors, the second step involves trying to include a first predictor in the model. So what we're going to do here, we're going to compare Pj for all j in 1 to p. So compare the performance P1. So P1 would be the performance with only the first predictor. P2 would be the performance with only the second predictor included, etc., until p small p being the performance with only the small p predictor included. And then what we're going to do, among all these possible predictors, we will define I1 being the maximizing argument of Pj. So here, this is not max, this is argmax. So argmax means select the j which maximizes Pj. So what that means is j is the index of the predictor which maximizes the performance with a single predictor included. Okay, so it's here this I1 is the index of the best single predictor, which is the predictor which leads to the highest possible performance when having exactly one predictor in the model. So here then, once we've identified I1, the best standalone predictor, then we're going to compare PI1 to P null. So if PI1 is smaller or equal to P null, it means that by adding any predictor, we would get an inferior performance to the model with no predictor at all. So in that case, incorporating a predictor just decreases the performance. So we're going to stop the procedure and say, well, the best thing we can do is to select exactly no predictors in our model. Okay. Conversely, if PI1 is greater than P null, it means that adding the predictor I1 improves the performance. So then we will include I1 in the model. Okay, so and now the current best model has shifted from no predictors to only the predictor I1. Okay, so now if this not satisfied, so if PI1 is greater than P null, we include PI1 and then go to the next iteration. So once we've included one predictor, then if the predictor was not included because it decreased performance, then the whole procedure stops and we select no predictor. Conversely, if we've included the first predictor because it increases performance, then what we're going to do in the next iteration is to try to include a second predictor along with the first one we've included. Okay, so what we're going to do here is we're going to compute PI1J. So we're going to take all possible predictors J and combine it with the predictor, the first predictor I1 we've identified in the first step, and compute the performance of all models which include both I1, the previous step optimal parameter or a predictor, and J, which is the new predictor that we attempt including, where J is any value between 1 and P except I1 because you cannot include twice the same predictor, of course. And then among all these choices of J, we define I2 being the Rmax of PI1J. So it's the predictor which gives the best possible performance when combined with the first predictor. Okay, so here PI1I2 is the best, the performance of the best model which has two predictor, but where we imposed that the first predictor had to be I1, which was selected in the first iteration or first step. So then what we do, we check the performance of our best two predictor model here and compare it to the performance of PI1, the best model with a single predictor. So if the performance doesn't increase by having two predictors, the best two predictor model, then we're going to stop the procedure and say, okay, the best model among all is PI1, the one which contains only the predictor I1 identified previously. Conversely, if the performance with the two parameters model is greater than the performance of the the single parameter model, then we're going to say, okay, we're going to continue. So our new optimal model or new current best model is the one with two predictors, I1 and I2. And then we'll go to the fourth step. And then we continue like this. So once we have two parameters, we try to include a third one. Look at if it improves the performance with respect to two parameter model. If it doesn't, then you stop and you say that the best is the two parameter model. Conversely, if a three parameter model is better than the two parameter model, then you include it in the model and then continue like this, trying to include new parameters until at some point, so until either two things can happen. Okay, so first thing is at some point, no new the performance doesn't improve further when you've included a sequence of parameters. So at this point, you just stop the algorithm and keep the predictors you've included. Or the other possibility is that eventually all predictors are included in the model, and in that case, the algorithm stops because you cannot include a new one within the model if you've already included all of them. Okay, so now why did we do that instead of comparing all possible combinations of predictors? Well, if we follow this procedure, then the maximum possible number of combinations of parameters that we will try in this algorithm is the following. So at the first step, when we had to test for the first parameter, we had p models to compare. Okay, so you include one predictor, you have p choice. At the second step, if you've included a parameter at the or a predictor at the first step, then in the second step you have p minus 1 possible predictors left to incorporate. In the third step, you have p minus 2 possible covariates to try if you have already included 2 in the first 2 steps, etc. So if in the longest possible outcome, which is if you've got to include ultimately all parameters or all predictive variables within the model, then the total combinations of predictors that you consider is p plus p minus 1 until plus 1. So this is an arithmetic sum, which gives p times p plus 1 divided by 2. So we can see that this quantity is of order p squared, which is much smaller than 2 to the power p. Okay, so as p becomes large, this quantity is much smaller than this. So you have much smaller amount of predictor combinations to compare than if you tried all possible combinations. So the advantage of using that stepwise approach is that you have much less combinations of parameters, or I always say parameters, but it's really predictors. So much less combinations of predictors to test than if you try them all. So it's much quicker to compute to determine what are suitable predictors if you use a stepwise approach. Okay, so it's much faster. But what is the downside here? The downside is if you use the stepwise approach, the model you ultimately retain might not be the best one. Okay, because sometimes it might be the case that if you have 2 predictors, either of them have very low standalone prediction ability, but when you combine them together, then they have very high predictive ability. Okay, so if that's the case, then at the first step, when you try to include one predictor in the model, then maybe the procedure will stop right away because all predictors have very low standalone predictive ability. Okay, but if you were the stepwise approach would say, okay, you have 0 predictors as your best case, but maybe the best case is in fact when you include both of them because they have very good joint predictive ability. Okay, so we see that ideally, if we wanted the best model, we would like to try all possible, so all 2 to the power p possible combinations of predictors to look at the performance of all such combinations. But in practice, it's often infeasible because 2 to the power p, as p increases, this term explodes pretty quickly. So the stepwise approach allows to only consider a subset of possibilities of predictor combinations, but this subset doesn't mean that you'll absolutely pick the best possible model, but it makes a lot of sense, and you gradually incorporate predictors it, based on like parsimony principle. So you only incorporate it if it improves your model with respect to the current model. So it's still a very intuitive, and it's a much quicker way to to determine the suitable predictors in the regression model. Okay, so this was the forward approach. In the forward approach, you start with the 0 predictors, and then you add a first one, and then add a second one until eventually you reach a point where no further predictor improves performance, and then you stop. There's another procedure called the backward procedure. Okay, so the backward procedure, it works pretty much the same way, but instead of starting with 0 predictors and including some in the model, you will start with all predictors in the model and gradually remove some until you stop improving the performance. Okay, so here I wrote, give a quick example of on the blackboard. This semester I don't have any blackboard, so I won't do the example, but it's pretty similar to what we did for the forward procedure. Okay, so if you have understood the forward procedure, it should be straightforward to understand the backward procedure. But the basic idea is, at the first step, you calculate the performance with all predictors in. In the second step, you try to you calculate the performance of all models which have all predictors in except one. Okay, so first model would be all predictors except the first one, second model would be all predictors except the second one, etc. Okay, so then you compare the performance of your original model with p parameters to the performance of all possible models with p minus 1 parameters, and if it improves performance to remove a parameter, then you drop it. If it doesn't, then you stop there and you keep all parameters and you proceed as such. So once you have p minus 1 parameters, you try to drop a second one and then a third one until at some point you end up not improving the performance of your model by dropping some parameters, and then you stop there. Okay, so one thing, just to recall something, make something clear, you might be thinking, well, if I'm dropping a parameter, shouldn't it always decrease the performance? Well, if you use in sample MSE as performance, then this would be yes. So you would never drop parameters. But now, because we've used a performance criterion, which let's say penalizes parsimony if you're AIC or BIC, or which measures predictive ability out of sample, it might indeed improve the performance to drop predictors if you, well, first drop the parsimony, and or if you use the MSE criterion, you reduce the amount of overfitting you do out of sample. Well, overfitting you do, which translates to better out of sample predictions. Okay, so we've introduced the forward approach, which is you start with no predictors and then you gradually incorporate some in your model. There's the backward procedure where you have all parameters in your model and gradually remove some. And then there's a third case where there are hybrid procedures which combine forward and backward iterations. Okay, so the hybrid procedure involves alternating between a forward step and a backward step. Okay, so in the hybrid procedure, so the typical hybrid procedure, you start with no predictor, then try to remove one, try to add one, then try to remove one, then try to add another one, then try to remove one, then try to add another one, then try to remove one, and you do this, you alternate between these forward and backward steps until eventually the model cannot improve performance neither by adding or removing any predictor, and then at that point you stop the procedure and keep the predictors you've included. Okay, so let's go back to what we said. So we can start with no predictor, the first step you would include a predictor. The first backward step, it's useless because if you've included the first predictor in the first step, of course you wouldn't remove it in the first backward step. Okay, so the first backward step doesn't make sense. Then second forward step, you might include a second parameter. And then the second backward step, well, once again, you can show that the second backward step is useless because you will not remove neither the one you've just included, and you will not remove the first parameter, otherwise it would have been optimal in the first place. But after that, after the two first backward steps, the subsequent backward step can make sense because what's the rationale for including possible backward steps in between the forward steps? It's because, and then this we describe here, some variables might have very high standalone predictive power, but very low incremental or additional predictive power when combined with other variables. Okay, so some variables might become obsolete once other variables are included. So we can see that for such variables, probably if you did only a forward step, they would be included very early in the model, in the selection procedure. But eventually, as you go forward, and maybe you incorporate other variables which make the first one somewhat irrelevant because the first one has very low incremental predictive ability with respect to these new ones. So because of that, it might make sense to try to remove some which become at some point irrelevant to make the model more parsimonious. Okay, so for this reason, some hybrid procedures do not only forward steps, but try alternating these with backward steps to try to remove predictors which become irrelevant or have low combined predictive ability or yield low combined performance, so as to make the model as parsimonious as possible. Okay, so that's great. This completes the description of the stepwise procedure for the selection of covariates. Now we're going to jump to another topic, which is interaction terms. Okay, so we've talked about combined predictive ability and said that some predictors might have high standalone predictive ability, but low incremental ability combined with others, and for some other variables it's the opposite. So it might be the case that for some variable its standalone predictive ability is very small, but the combined predictive ability of that variable with the second one might be very high. So in that case, you want to be able to capture these interactions between the predictors. Okay, so if two predictors interact together, if you have a linear model and just use the original predictors, because of the linear relationship, you won't be able to capture the interplay between these two parameters. So what you typically need to do is to introduce interaction terms. So let's give an example here. Okay, so what you can do here to incorporate interactions within these models, you need to, one way to do that is to take the product of two existing predictors to select, to create a new predictor which captures the interaction term. Okay, so for example, if you have a predictor xi and xj, then you can define a new variable called xij, which you can define as xi times xj. Okay, so this creates a new variable within your data. And why do we say it can capture some interaction? It's because let's say xi and xj have either the value -1 or 1. Okay, so xi can be -1 or 1, xj can be -1 or 1. Then maybe one case that could happen is that the target or the response might be very large if both are 1 or both are -1. So both very high at the same time, or both very low at the same time. If you use a regular linear model for that and you just use xi and xj within the model, you won't be able to capture this relationship, okay? Because if the slope for xi is positive, for example, you will have high values when xi is 1, low values when xi is -1 as prediction. So you won't be able to capture the case that you will have high predictions when both xi and xj are low or -1. Conversely, when you have the xij term, then what's going to happen is that if xi and xj are both 1, then the product will be 1. If xi and xj are both -1, the product will be 1. Okay, so we can see that this interaction term, it's worth 1 if both are +1 or both are -1, whereas if either one of them is -1 and the other is 1, then the product will be -1 and will be low. So we can see that this new predictor is high if both variables are high or both variables are low at the same time. So we can see that you can capture, this predictor captures interaction between two variables, and you can have phenomena, or you can have a linear model where using this new predictor, you can represent situations where your prediction will be low or high depending on if you have both being small at the same time or both being high at the same time. So in that case, if you have a situation like that, the interaction term xij might be more effective to make predictions than either xi or xj individually. Okay, but now, so we're going to see that if you have p predictors originally and you try to add potential interactions as new predictors, this inflates the total number of predictors even more. Okay, so if you have p predictors, the possible number of twofold interaction terms, predictions between, or products between two predictors, is p times p minus 1 divided by 2. Okay, because for the this is choose 2 among p predictors. Okay, so if you want to have a regression model where you consider all standalone predictors p and all twofold interaction products, then you would have p plus p times p minus 1 divided by 2. So you have something of the order p square predictors to consider. So this is a lot more parameters to incorporate in your model. And if you want even higher order interactions, so let's say products between 3 variables or something like that, then it's even many more covariates or predictors to be included, because if you have you want interactions of order k, there are choose k among p possible such interaction terms that can be designed by choosing all the ways you can choose k predictors within the p ones. So now you started with a data set with p predictors. Now by including interactions, you might get a number of predictors with an order p to the power 2 if you have 2, or maybe p to the power 3, or if you use order k interactions, something to the power like p to the power k. So by augmenting data set and including interaction terms, if you want to reflect interactions, this substantially increases the dimension of your data set. So for that reason, if you want to do a regression and you want to incorporate potential interactions between variables, it's even more important to resort to stepwise model selection procedures. Okay, because if you have, instead of having p predictors, you have something to the power p2 predictors by considering 2 by 2 predictors. If p is equal to 100, p to the power 2 would be 100 to the times 100, so 10,000 predictors. So then you cannot, so if you tried every possible combination of predictors, including interactions, you would get a total of 2 to the power 10,000 models. You cannot compute the performance for them all. So when you include interaction terms, it becomes even more critical to use these stepwise procedures instead of considering every possible combination of parameters. So you need to select suitable combinations that could make sense, and the stepwise procedure can help you out to do that in a way that is feasible in terms of computation time. So just as a quick reminder, the reason why we wanted to do this to include to select predictors within a regression model instead of keeping them all is because we wanted to reduce the variance as much as possible, because the variance, we signed the variance bias trade-off, that to get the best expected square error for new observations you predict, you need to have both small variance and small bias. So if there are predictors which are not very helpful for prediction, they won't help you reduce the bias, but they generate variance by generating noise, so you'd rather remove them. So what we did here is, by trying to remove these unuseful predictors, is trying to reduce the prediction variance. Now, predictors or covariate selection is one way to reduce the variance of your predictions, but it's not the only one. So in the next part of the chapter, we will discuss shrinkage methods, which are other ways to reduce the variance of your predictions, but this will be for the next lecture. So I'll stop there today. Have a nice day, take care, and I'll see you for the next video.